every single time you pick up a coffee cup, tie your shoelaces, or grab your phone off the nightstand, your brain fires off a signal. It travels down your spinal cord, through a tangle of nerve junctions, and out into the muscles of your hand. And you never think about it. Not once. It just happens, thousands of times a day, completely free. Now, here's the number that changes how you see that. Health researchers estimate that somewhere between 250,000 and 500,000 people are paralyzed by spinal cord injuries every single year, worldwide. That's roughly a city the size of Tampa or Sacramento every year who may never grab that coffee cup the same way again. Stack just 20 years of that number together, and you're looking at more people than live in Australia. And until very recently, every single one of those people, anywhere on the planet, had exactly 0 approved options for getting that hand function back through a brain implant. Not in the US, not in Europe, nowhere. So when China's National Medical Products Administration quietly approved a coin-sized brain implant called NEO, built by a Shanghai startup called Neuralink Technology, working with a research team at Tsinghua University for actual commercial sale in hospitals, not trials, on March 13, 2026, that was worth paying attention to. And when, just days after that approval, the same device was assigned an official billing code inside China's national health insurance system, the kind of bureaucratic step that normally takes years on its own. That was the moment this stopped being a science story and started being something else entirely. If you're into stories about technology quietly rewriting what's medically possible before most people have even heard the name involved, hit like and subscribe so you don't miss the next one. Now let's get into how a company almost nobody outside China had heard of just beat Elon Musk to market. For nearly 20 years, the gold standard in brain-computer interfaces has been what's called an intracortical electrode array, tiny needle-like sensors, thinner than a human hair, inserted directly into the brain's motor cortex, sitting right among the neurons themselves. This is the approach used by research consortiums going back to the early 2000s, and it's the approach Neuralink has built its entire reputation on. And to be clear, this isn't a dumb approach, it's arguably the smartest one. When you're sitting directly inside the tissue that generates the signal, you get extraordinary resolution, enough to decode individual neurons firing, enough for a paralyzed person to move a cursor with the kind of precision that looks like science fiction. For 2 decades, this has been the frontier, and the people working on it are some of the most careful, rigorous scientists in the world. So why hasn't it reached a hospital near you yet? The honest answer isn't money, and it isn't bureaucracy for its own sake. It's biology. When you place a rigid electrode inside living brain tissue, the brain treats it the same way it treats any injury. Specialized cells called glial cells, think of them as the brain's cleanup and repair crew, migrate toward the foreign object and slowly wrap it in a thin layer of scar tissue over the following months. That scar tissue is electrically insulating, so the signal that was crystal clear on the day of surgery can become muddier by year 2 and muddier still by year 3 as that sheath thickens. This isn't a flaw in any one company's hardware, it's a property of how mammal brains respond to anything that punctures them. And it's the single biggest reason every regulator on Earth has approached invasive brain implants with such extreme caution. Because you genuinely cannot know whether a signal will hold for 10 years until you've watched it for 10 years. That caution shows up in the numbers. As of January 2026, after years of careful FDA-supervised trials, Neuralink had a total of 21 human participants enrolled. 21. Not because the team isn't talented. By most accounts, it's one of the most well-resourced BCI teams on the planet. But because the entire intracortical approach demands that kind of slow, one patient at a time pace. That's simply what the biology requires if you're going to do it responsibly. So the question that nobody had fully chased down, the question sitting underneath 2 decades of brilliant, careful scar tissue fighting engineering, was disarmingly simple. What if you didn't need to go inside the brain at all? What if the signal you actually need is sitting right there on the surface, waiting for someone willing to stop trying to get deeper? Picture the operating room in Beijing where a man known publicly only as Dong is lying on the table. He's been paralyzed below the neck for years. A cervical spinal cord injury, the kind that leaves the shoulders and upper arms working, but the hands essentially silent. The surgical team isn't drilling down into his brain. They're not threading anything into the gray matter itself. Instead, they're placing a device about the size of a coin onto the surface of a tough, fibrous membrane called the dura mater, the brain's own natural protective wrapping, the layer that sits between the skull and the brain tissue itself. The whole procedure takes just over 90 minutes. Compare that to the longer, more delicate surgical windows required for devices that have to be threaded directly into living brain tissue, millimeter by millimeter, and you start to see why this detail matters. Here's a way to think about what Neo is actually doing differently. Imagine you're trying to figure out what a packed stadium is chanting. One way to do that is to walk onto the field with a microphone and hold it up to each individual fan's mouth, one at a time, collecting incredibly precise recordings of single voices. That's the intracortical approach. Extraordinary resolution, neuron by neuron. But there's another way. You could just stand at the edge of the stadium and read the wave of sound rolling through the crowd as a whole. The rhythm, the surges, the pattern. You lose the ability to pick out any single voice. But it turns out that for a huge range of practical tasks, telling the crowd's chant apart from their silence, telling open hand from closed hand, the wave is enough. Enio's 8 sensors sit on that membrane and read exactly that kind of wave. Population-level electrical activity moving across the surface of the motor cortex, rather than the firing of individual neurons underneath it. An external device picks up that signal wirelessly through a small coil worn on the skull. A decoder translates the pattern into an intention, open hand, close hand, grip, release, and that command gets sent to a soft robotic glove that actually performs the movement. Brain signal in, glove movement out. That's the whole loop. And here's where the first flip in this story lands. For nearly 20 years, the entire BCI field operated on an assumption that felt so obvious nobody questioned it. The problem was depth. Get closer to the neurons, get a cleaner signal, get better control. More invasive meant more capable, period. The actual bottleneck wasn't signal resolution at all. It was that the depth itself, the act of puncturing the brain, was the thing creating the long-term obstacle by triggering the very scar tissue response described back in Section 1. The weak link in 2 decades of brain implant research wasn't the decoding software, or the electrode materials, or the surgical technique. It was the simple fact of being inside tissue that the body is biologically programmed to wall off. NEO doesn't fight that response. It just never enters the territory where that response gets triggered in the first place. It sits on the wall the brain already builds for itself and reads through it. The results from this aren't anecdotal. Since October 2023, Neuralink has run 36 separate clinical procedures using NEO, and the bulk of those, 32 of them, happened in just a few months during 2025, an acceleration that itself tells you the team had moved from "does this work?" to "how fast can we repeat it?" Dong's own recovery followed a pattern that's become typical. Roughly 2.5 hours of training with the device each day, and by the 9th day of that training, he grasped a ball with his own hand, no glove involved at all. That was a miraculous moment, he said afterward. And in a signal of exactly the kind of transparency this story needed to be taken seriously, the details from one of the very first in-person trials were published as a preprint, openly accessible well before the commercial approval ever happened, meaning outside researchers could pick apart the methodology long before NMPA made anything official. A piece of regulatory paperwork is one thing. A hospital actually doing the procedure on a real patient under real pricing is another thing entirely, and that's exactly what happened at Wuhan Tongji Hospital in December of 2025, months before the national approval even landed. This was the first surgery performed anywhere under China's new government-guided pricing framework for the device, meaning regulators had already gotten far enough into the process to start setting official prices, even while the broader approval was still being finalized. That procedure was funded through research grants rather than patient payment, but the timing matters. It means the 90-minute procedure time, the recovery trajectory, the grasping outcomes, All of it was being tested in an ordinary hospital setting by an ordinary surgical team, not a hand-picked flagship lab. And the outcomes lined up with what the 36 trial dataset had already predicted. No surprises, no outliers requiring a press release explaining them away. Just the same numbers in a new building with a new team. Now, the pricing detail is worth sitting with for a moment because it's where the headline number actually comes from. The government set the official procedure service fee, the surgeon's fee, essentially, at around $900. That's the figure that's been getting attention. But that's not the full cost of getting this device. The device itself plus the full procedure currently runs somewhere between roughly $41,000 and $69,000. And as of now, that portion isn't yet covered by government health insurance. So the honest version of the story isn't China made a brain implant that costs $900. It's that China has, for the first time anywhere, put an official government price on the labor of performing this surgery, which is a very different and arguably more significant kind of milestone. It means the system has moved from, is this legal, to what should this cost, which is a question regulators only ask about things they expect to scale. Now, I know what some of you are thinking. One hospital, one pricing framework, one country's regulator moving fast on one company's device. That's not proof of anything beyond a single bet paying off. Fair. So look at what else is happening in parallel, at different companies, doing different things with the same underlying shift. Neurozess, a separate Chinese BCI company working on a different application entirely, using brain signals for direct computer control rather than robotic glove grasping, has already completed 54 separate surgical procedures. Not 36. 54, across a different patient population, solving a different problem with different hardware. That's not one company's lucky break. That's multiple teams, multiple approaches, multiple hospitals, all moving through the same suddenly open regulatory door at roughly the same time. Strip away the regulatory filings and the funding rounds for a moment, and what this story actually comes down to is a small rehabilitation room somewhere in Beijing on what is, on paper, just another Tuesday. Dong sits in a chair facing a table. On the table is the glove, soft, segmented, a mess of thin cables running back to a laptop. A technician sits beside him, eyes on a screen that's mostly noise, a scrolling waveform, a confidence percentage, numbers that mean almost nothing to anyone outside the room. For the first 8 days, this is the whole routine, and it is almost aggressively unglamorous. The technician fits the external reader against Dong's skull. The laptop boots the decoder. Dong is asked to think about closing his hand. Just think it, the way you think about closing your hand before you actually do it. And the glove twitches, or doesn't, or twitches at the wrong moment. The technician adjusts a threshold. Tries again. There's a lot of waiting in this room, a lot of again. A lot of 2.5-hour blocks of time where, from the outside, it looks like nothing is happening at all. By day 9, something has shifted, though nobody in the room could tell you the exact moment it happened. The technician runs the same calibration sequence. Fit the reader, boot the decoder, think about closing your hand. But this time, before anyone reaches for the glove, Dong's own fingers move, not the robotic ones, his. They close, slowly, around a ball sitting on the table in front of him. The technician's eyes go from the screen to Dong's hand and back to the screen, like they're checking whether the two things are actually connected, or whether this is some kind of mistake. Dong holds the ball. Nobody says anything for a second. Then Dong says it. That was a miraculous moment. Not because the glove worked, because the glove wasn't even on. That's the contrast this whole story rests on. 8 days of a man and a technician staring at noise on a screen, making tiny adjustments, waiting through hours that felt like nothing, and then one ordinary Tuesday, a hand that hasn't moved on its own in years, closes around a ball, with no machine touching it at all. While that was happening in a rehab room, a much louder reaction was happening on trading floors and in venture capital offices across China. Within days of the NMPA's approval, shares of Hong Kong-listed BCI-related companies, Sanbol Hospital Management Group among them, jumped more than 10%. That's not a reaction to a press release about the future. That's a reaction to a price list, and the money kept moving. Shanghai-based StairMed, which is building a different kind of implant, soft, flexible electrodes placed by a surgical robot, closer to Neuralink's intracortical approach, closed a 500 million yuan funding round, roughly $73 million, led by Alibaba Group and backed by a stack of funds including SDIC, OrbiMed, and Kimming Venture Partners. StairMed says it plans to implant 40 more patients this year. Meanwhile, Hangzhou-based BrainCo closed a 2 billion yuan round in January. Neurosess, working on brain-to-computer control rather than robotic grasping, has already pushed past 50 surgeries. And Gestala, in Chengdu, raised 150 million yuan for a completely different approach, non-invasive, ultrasound-based, no surgery at all. Here's the thing worth sitting with. This is not happening because investors suddenly develop strong feelings about disability rights. This is not about following a trend. It's about staying in business. China just became the first place on Earth where a company in this space can point to an actual regulatory pathway, an actual insurance billing code, and an actual government price list, and say to an investor, here is how this becomes a real business, not just a research program. Every dollar moving into this space right now is moving because that pathway exists, and it exists in exactly one country. Now, here's the part that should make policy analysts, not just investors, sit up straight. This isn't really a story about who builds the best wheelchair replacement glove. The bigger implication is about precedent. Whoever runs the most procedures first, accumulates the most long-term safety data first, and builds the manufacturing pipeline first, doesn't just win a market. They end up setting the de facto global standard for what a safe, approved brain implant even looks like. The same way early movers in any new device category tend to write the playbook that regulators elsewhere eventually borrow from. Neurosess's work on direct computer control is a small hint of where this goes next, because once a regulator has approved reading population-level brain signals for one purpose, the case for a second purpose gets easier to make. Let's be honest about the obstacles, though, because they're real. The $900 figure that's been circulating is the government-set surgical fee, not the cost of the device itself, which still runs somewhere between $41,000 and $69,000, and which isn't yet covered by insurance. The clinical track record only goes back to October 2023, which means there's no data yet on what these signals look like after 10 or 15 years. The very question that made regulators elsewhere so cautious in the first place. And regulatory bodies in the US and Europe don't simply import another country's approval. They run their own evidentiary processes on their own timelines. None of these challenges change what the underlying data shows. They just define the gap between what's now technically and commercially possible and what will actually reach most patients and when. Even so, look at the scale math. Somewhere between 250,000 and 500,000 new spinal cord injuries happen globally every single year. If even a tenth of those patients, 25 to 50,000 people, in a single year, eventually became candidates for a device like this, even at the current unsubsidized cost, that's a market worth well over $1 billion annually from new cases alone, before you even count the tens of millions of people already living with these injuries. And there's a second number underneath that one. Every hour of caregiver assistance that a restored grip replaces is an hour that doesn't have to be paid for, scheduled, or staffed. Multiplied across hundreds of thousands of households, that's not a medical story anymore. That's a labor market story. So zoom back out. This video started with the idea that the problem with brain implants was always about getting deeper into the brain, and it turned out the depth itself was the obstacle all along. And it's ending with the idea that this is a story about restoring hand function to paralyzed patients, and it turns out it's actually a story about who gets to write the rulebook for the entire next category of medical device, simply by being first to put a price on it. Here's the one-sentence version. Neuralink is still calibrating its 21st patient under FDA supervision, and China just put a government price tag on the surgery for its own version of the same technology. If this changed how you think about a story you probably scrolled past in your feed without a second look, give it a like. That's genuinely the only signal that tells us this kind of story is worth doing again. And if you want more videos that dig past the headline on China's tech and geopolitical moves, the ones that quietly matter more than the ones that get the loudest coverage, subscribe and turn on notifications so you don't miss the next one. And here's what I want to hear from you in the comments. China got this into a real hospital with a real price, years faster than any Western regulator has moved on anything similar. And a man got his hand back because of it. Is that a system working the way it's supposed to, getting help to people faster? Or is the slower, more cautious approach elsewhere the thing that's actually protecting patients, even if it means people wait years longer for something that already exists somewhere else? Two very different ways of looking at the same speed. Drop your honest take below.